Log on, tune in, find out. Another good idea from Cambridge.
To the morning session. Our first speaker this morning is Emma Previato from Boston University, going to talk to us about isomonodromy and integrability.
Thank you. Let me make sure I thank the speaker. I thank the organizers very much for the honor and the opportunity to try and learn so much this week. I feel a little bit like my current PhD student. When I organized her first public lecture at the Clay Institute, I said the night before, "So are you excited?" And she said, "Well, my entire bibliography would be sitting in the audience." So I feel the same way. Also, I have to apologize, possibly because I woke up and I can't hear anything. Like when you fly, sometimes you have an ear completely stopped. I hope you can hear me. Okay, so let me tell you what I'll do in the talk. This is the most speculative talk I ever gave, as you can see from the number of question marks. The first is not a section, it's section 0, and that will be very much a speculation about two curves. Then in the second one, I will try to relate two problems which are in a sense understood, but I don't think explicitly. One is isospectrality and the other one is isomonodromy, and with examples. And then to try and abide by the theme, I will show some special functions, why they arise. And then parts 2 and 3 would really have been the original project, which supposedly I should have showed you, but I haven't been able to complete it. And then part 4 is another excuse to be talking about special functions, and it's a new solution to the dispersionless KP hierarchy. So let's start. So first of all, the speculation. I think the challenge for me currently is to understand why there are basically two types of KdV equations. So one is isospectrality, and that's the motivation because that's very old and well understood. And the other one is something that came up recently in the context of the Virasoro constraints and the Witten-Kontsevich equation. So I thought I'd show you what they are because you hear a lot about them if you haven't worked with them. There is this function g, which is, you see the intersection number of these topological classes on moduli spaces of curves, the generating function. And notice that the times ti from 0 to infinity. And these are the Virasoro operators. So they differentiate in time up to order 2. And the Virasoro algebra constraints. And then what happens is that the exponential of g is the tau function for the Korteweg-de Vries hierarchy. So what was proved very recently, and everybody is excited about it, is that by using random matrices, Einard and Orantin, we're able to show that the recursion rules for the Kontsevich integral, that's function z of tk, recursion in k, are the same as the recursions for the volumes of the moduli spaces, depending on the length of the geodesics of which you cut on the Riemann surfaces. And the formula is given by a Laplace transform. And this is something that I really would like very much to understand because I think it's a relationship between the two types of KdV equations. So they just produced it by just staring at the invariants. So in that way, they related their spectral curve for the random matrix invariance, which, as you see, is a plane curve in x and y, but it's not analytic. It's not algebraic. It's analytic, and the Kontsevich curve. Okay. So what is the KDV curve in the traditional isospectral theory of KP? The curve arises because there is an isospectral deformation of this formal pseudo-differential operator whose coefficients solve the equation, Kp or KdV, which is a reduction, as you know. And what is the curve? So I thought I'd remind you, it comes up in a very simple way in differential algebra. You take, for the curve, the spectrum of a ring of commuting ordinary differential operators. And the ring arises in a very pretty way and in a very classical way. You take functional coefficients which can be of various types. I'll omit this discussion. They could be analytic, or they could be rational, or by translation you can make them all regular at one point, which I don't think is a trivial fact. It's a fact of differential algebra. Then if you normalize one of the elements in this ring, you can then formally write an nth root of this operator. And then Schur in 1905 proved that the centralizer is going to be just power series with constant coefficients in that formal pseudo-differential operator. So because they have constant coefficients, you can see that there can be no more dimensions to it than a curve. Okay, so that's the isospectral curve. And some examples which you've all seen, the N's Delamé equations, KdV operator with special integral coefficients times a Weierstrass P function, Halphen. Here you want a third order operator, and then the isospectral deformations would solve the Boussinesq equation. And again, you can write all the coefficients in terms of elliptic functions. So there is some very nice classical theory about elliptic coefficients and commuting operators. So Burson and Chondi, who studied, if you wish, a completely formal problem of finding all the commutative subalgebras of the ring of differential operators, completely solve the problem provided those algebras have rank 1 in a technical sense, and they are all isomorphic, all these algebras, to points of, they all correspond to points on the Jacobian of the isospectral curve. So that's a very pretty algebraic story which was understood at the beginning of the 20th century. Now, very recently, we have the D equations, which is not a pun for discrete, it's dispersionless. In the dispersionless theory, there seems to be a completely different curve. And for example, you can solve the string equation, again for formal pseudo-differential operators. And there is some beautiful work by a student of Takhtajan. And what is the curve? Well, the curve only appears as an analytic neighbor of infinity, and the expansion of f and g to univalent functions which establish some uniformization of this neighbor have the same expansion as L and L tilde. So this is really my obsession now, to understand these two curves. Anyway, let me show you now finally a little bit of isomonodromic story. Here is the history. If I understand correctly, it begins in 1963 when people find solutions for the Ising model that can be expressed by Painlevé transcendence. So then a little bit later, there is a solution of the Dirac equation in terms of Paine-Levé transcendence by Satomi Wajimbo. And what happens is that in order to go from the Dirac equation to the isomonodromy problem, which is Paine-Levé 3, which is shown to be equivalent, you again use a formal Fourier transform between the variables. This is a two-vector, so there's a two-vector W, and you transform into a two-vector square root of u and square root of u minus 1. So that's the speculation. Now, section 1. How do we relate more consistently integrability and isomonodromy? Well, my answer is that I don't know, but I'm here to learn from you, so there will be lots of questions. The isospectral property, which is what I call integrability alternatively, is something I understand and is well understood. So it begins when you take the isospectral deformations of the pseudo-differential operator, which gives you solutions to Kp. There so happens to be a nice class of algebro-geometric solutions, and so those correspond to some cases of stationary solutions. What does that mean? It means, for example, that a power of this pseudo-differential operator becomes a differential operator, and therefore all those, you see, because sub plus means truncating and taking positive coefficients, all those powers commute with L. Or more generally, you can have a linear dependence, so constant combination of powers belongs to this ring of differential operators. If that happens, it's not hard to show that all the coefficients of these specific solutions, these stationary solutions, can be written in terms of special functions. And so I thought I would show you one occurrence of special functions in isospectrality. And you do that by solving the inverse spectral problem. So you assign the spectrum and you construct the operators explicitly, and that was done by Krichever in 1977. You take any Riemann surface, a bunch of points, and some normalization, again, uniformization at infinity, but only holomorphic at this time. That uniformization plays the role of the inverse of the spectral parameter, and then you construct an eigenfunction explicitly in terms of theta functions, and that eigenfunction psi, you see that there is an exponential times multiplied by the inverse of the spectral parameter times a quotient of theta functions which encode the zeros and the poles of the eigenfunction. That eigenfunction is a common eigenfunction for the entire spectrum of commutative rings, and then when you deform in time, for the deformed commutative ring. And this is what people mean by saying that the this Hamiltonian partial differential equation Kp has been linearized because the dependence on time has become linear on the abelian variety, where you take the theta function. So that's well understood. Now, what I don't understand is the isomonodromic deformations. So they started having something to do with integrable PDEs, I think, with the observation by Ablowitz and Seeger in 1978 that there are subsimilar solutions of KdV which, when you write the corresponding ODE for those subsimilar solutions, they now are functions of one variable, and you apply a Mura transformation, you obtain Paine-Levé 2. So Ablowitz and Seeger launched a program of linearizing ordinary differential equations that have the Painlevé property, essential singularities of the solutions and branch points are fixed, are not movable. So those typically nonlinear ODEs you can solve now by inverse scattering transform using the inverse scattering using the kernels that had been used to solve the, for example, this kernel is used to solve the KdV equation, you see, through this type of nonlinear Fourier transform, which is something they had discovered. On the other hand, if you do the Galilean transformation, you can reduce KdV to Painlevé 1 if you just do a trick and reduce to one variable again. So my question is there any way in the world to predict which of the Painlevé equations you can associate to a given PDE? And I have not been able to find any answer in the literature. So I started studying, doing a case study with a graduate student at Boston University, Nick Bennis, and I think that because of being at this program, we can write a little we can write a little construction, which I'll come to in a second. So let me show you what we found in our case study, that there were several reductions of Kp, and these authors typically didn't cite one another, and they were all found by a variety of methods. So the most consistent way of finding similarity reductions, again, there are many experts in the audience, it seems to be the method of Lie invariance. So you have a recipe that tells you what's a deformation, a little bit like in Evelyn Hubert's talk yesterday, and also Elizabeth Mansfield is an expert, and Peter Clarkson. You say what the deformation of the PDE could be, and then you solve. But typically you solve a system of nonlinear ordinary differential equations, so you don't know if you found all the solutions. And all these different authors were coming up with different solutions, and they were reducing first Kp to Boussinesq or KdV, and then therefore with a second reduction they were finding Painlevé 1 or Painlevé 2. There is another author who earlier, nobody seems to quote him, had gone from Kp to a Painlevé equation in just one shot by using again the idea of the inverse scattering. And he found the transformation by hand. He found P2. So then there is another later author who adapts an idea of Clarkson and Kroskal, who do a direct, without studying all the invariance, group actions that leave the equations invariant, study directly some similarity reductions, and he finds again just Painlevé 1 and or Painlevé 2. And then there are conditional symmetries that have been studied. I don't know if you can do a complete solution. Conditional symmetries means that the equations are not invariant, but there are still similarity reductions. Again, Dr. Clarkson is an expert. So what I found a little bit more friendly was an algebraic linearization of these Painlevé problems, which Flaschka proposed in 1980, and following the discoveries of similarity reductions and relations with Painlevé. So this is what he proposes. He has again a solution by inverse scattering. He phases time out of the Marchenko kernel, And then he comes up with something which is an algebraic equation, which I think nobody in differential algebra has studied. So remember that earlier on, I said differential algebra formally can study the equation of commutation of two ordinary differential operators, Ls equals 0. Then more recently, string equation is interested in solving the equation Ls commutator equals 1. I don't think anybody has studied this equation, which Flaška derives from the condition of the inverse scattering for a PDE. And then by scaling time out, he proposes as a linearization of a Penlevet type ordinary differential equation. The algebraic equation is L equals Ls. So again, the commutator, the derivation in the algebra of differential operators, belongs to the ideal generated by L. So then he gives just the KDV example in that short paper, and he tells you what the operator T plus B is. You see, it's not the one like which would be B that commutes with L, as I showed you before, but it's a deformation. There is a plus 1/2 x derivative with respect to x, and so this is now the algebraic condition, L equals commutator Ls. Okay, so my question here is whether it is possible by a completely algebraic condition to obtain a Penlevet type ordinary differential equation. And with this student, I think we are doing some constructions thanks to a Krichever, again, kind of inverse spectral problem, which I'll show you in a moment. Let me explain a little bit the rationale for Flaška's construction. So he, in his examples, yes, I can't hear you, but please do.
Okay, I try to speak loud. So when you say algebraically, you mean
Yes.
that you sort of fix one of the two operators and you look at all the ones which
solve that equation.
Okay.
Yes, yes.
So
yes.
just looking at the
Inside
algebraic
this ring of differential operators in which the operations are non-commutative. I don't think it's been studied at all.
No, it's normally you do analytic approach and you study the behavior at infinity and then
Right. So I think it's a very beautiful thing, and Flaška meant to write a lot more about it. That's what he announces, and then he never did. So I think, since 1980, there may be a point in studying this problem per se, and I'll show you some constructions in a moment. So, but again, he calls them speculations. He speculates a little bit about this equation. He says, what is the significance? So first I wanted to show you how he presents it. So he says, if I have, if I make a choice of two vacua that work trivially, as people were doing at the time for the isospectral deformations, let's just take d squared, the derivative without coefficients for L0, and d cubed for B0. So then they commute, right? That's safe to say. And then you would take the time deformations satisfying this equation. But then he says, I want to find this T0. Well, if I know a priori these Volterra operators, K plus and K minus, then for the PDE, then my condition is the following, that x times I plus k plus minus I plus k minus should be equal to x0. And then I solve for x. And he only does it in one example. And now these are, remember, pseudo-differential operators. So again, I'm advocating solving that by a Sato kind of formal pseudo-differential operator, maybe by recursion, and then seeing what happens if this equation holds. If this equation holds. Flaška says that if you can solve it, then it does hold. but he starts with some interesting operators to begin with. Okay, so now a key to answer, I think, would be to find a Kirchhoff kind of inverse spectral construction, in the sense that you give yourself an eigenfunction. You give yourself an eigenfunction psi, because that's the way you recover the coefficients of the pseudo-differential operator, and therefore the solutions to the Kp in terms of theta functions. So what is an eigenfunction? And this is the second piece of speculation that Flaschka gives in that short paper. He says, what does this condition mean? So if zeta is an eigenvalue and v is an eigenfunction for L, what does this algebraic equation mean? Well, he massages a little bit, and he says it means that there is a polynomial expression in the spectral parameter such that when you apply it to the eigenfunction, you get zeta times the eigenfunction. A derivative with respect to zeta. And you'll see that in a moment again in isomonodromy problems. So he stops there. Okay, so I'm going to propose a little bit of a construction. So then there is a paper at the same time by Flaschka and Newell. And again, they say that this is part 1, 1980, and they never came up with part 2. And what they want to do is exactly what I'm trying to do, if it makes any sense, really link isomonodromy and isospectrality in some kind of consistent way. So this is what they say. They say, suppose I start with my zero curvature conditions for integrability, so for isospectrality. Suppose that I deform some PDE problem in time, and I have these conditions of compatibility. So then they're using a vector notation here, and is in the AKNS model. Then they say the finite gap solutions, the ones that we can solve in terms of special functions, are given by this constraint, which is equivalent to the one I showed you before. There is a stationary condition. And then they show you the spectral curve, which is the determinant of, these are the coefficients now, of these matrices, and you want a spectrum of that. So it becomes a curve in the plane using the spectral parameter zeta and some other spectral parameter lambda. Okay, so the constraint is on the eigenvector. The constraint on the eigenvector does this. Now, what is isomonodromy? Isomonodromy is differentiating this eigenvector with respect to the spectral parameter. And now if you regard the times as parameters, this is the equation which you want to solve, and it becomes an ODE, and this is the Painlevé problem. This is the Painlevé problem. Now they even give a clue in some special examples to these self-similar solutions, which for me are so mysterious. It's just so clever. You just construct these special group actions under which the equation is invariant. These self-similar solutions actually are written for you from the characteristics of this ODE. At least they show one example. So now, more generally, they study these Painlevé type ODEs as a monodromy problem, so with Stokes sectors, and they show, again, just in a couple of examples, that they can solve the equations. They can solve the equations, and so the philosophy here is to linearize these Painlevé type of problems and solve them. But the solution is to be concrete, has to be an educated guess. You can solve them in terms of Airy functions. You can solve them when you solve the gluing conditions on the Stokes sectors. they advocate that there should be a theory of multi-phase self-similar solutions, so solutions for these Pain-Levé problems associated to the higher times of the isospectral deformations, and that this class of solutions should become very important. And that's why they call it part 1, but there is no part 2. So in a way, I do think that there should be a closer relationship between at least certain equations of integrable PDEs and certain monodromy problems.
Can you,
Please.
sorry.
No.
So you're talking about essentially the dependence of the Pain-Levé on the T, which is left there or not?
As parameters, I don't think so. The Pain-Levé is still becoming, is still a function in, the Pain-Levé condition is still an ordinary differential equation. Nevertheless, for example, if you look at the higher KdV flows in the hierarchy, you obtain a different Pain-Levé problem. I think that's exactly what they mean by multi-phase.
It's higher order, and you inherit
Yes,
some
higher
of the
order.
T's
Yes.
are still there.
Yes.
So
You inherit some of the T's. I'll show you in the equation in a moment.
yeah.
Yes, you do inherit the T's. Yes. Not as variables, but I'll show you exactly how, I hope, if I understand it. There is a remark here which links the story to the Garnier system, which I want to show you. So the remark is that if you make an autonomous limit and you set for all the T's this relationship, you let this T go to infinity, then the zeta equation which we saw earlier, this one with the T parameters, becomes exactly the algebraic constraint for the finite gap solutions. And so I also think that's very tantalizing. Here's the spectral curve which we saw before. In this autonomous limit, you immediately want to do a WKBJ approximation. Not me, but you, because supposedly you know what that means, and because T is going to infinity. And if you do that, the iconal equation of this W whatever is the spectral curve. So again, I think it's a little miracle that they leave that, so the relationship between these two curves, okay? This isomonodromy property. I'm not sure if I see the T's in the isomonodromy problem.
You do.
You do.
You do. Well,
Excellent.
there is a way to, normally in my, we normally put them to 0, but in fact it's a choice, and you can choose not to, and you can then produce isomonodromic problem for the hierarchy with the T's.
Yes. So I think that would be an interesting class of equations and solutions to study, as they say. And the last tantalizing remark that I want to quote from that paper, I have to read it to you. It's so beautiful. There is a remarkable principle so far not really explained, and this is 1980s, but I don't think it's explained yet, but supported by all the examples known to us. The nonlinear equations arising from monodromy preserving deformations are not autonomous. Replace the explicit independent variable by constants. The resulting autonomous equations are solvable in terms of abelian functions. So we want to understand that. Okay, so Krichever looks at their paper and says, oh, neat. Now I can construct these things because I start with the Lax pair, but basically he says I'm not doing anything different, and I think he's right. And here I'll just tell you, instead of going through the formulas, that what he does is he takes P1 and he creates these Stokes sectors. So basically he has only two singular points, 0 and infinity. he creates these gluing matrices which allow the eigenfunctions to go from one Stokes sector to the other one. You see the plus S minus S. S is an indexing for the Stokes sectors. And then there should be an M, a monodromy, that relates the gluing matrices, a monodromy condition. And then he says, if I do all this, I can solve with, you see, a psi function, a little bit like the Baker function from before. Then he says, if I want to, I can give these specific eigenfunctions zeros and poles as I had done before. And these are the conditions on the zeros and poles, just a bunch of complex numbers. And so instead of just this eigenfunction with these assigned monodromies across the Stokes sectors, he says I can associate a vector bundle over P1, and that I can prescribe a vector bundle over P1, and then to each of them an eigenfunction. So that would be nice. It would be a larger class of algebra geometric solutions for the isomonodromy problem, except the self-similarity only arises if he takes those vector bundles to be line bundles. So if you increase the rank of the vector bundle, if you give yourself more geometric objects, you don't have immediately the self-similarity, but I think you could, you see, which is just written in the previous prescription. He says that the dependence of the eigenfunction as an exponential in time and x and lambda should have this self-similarity written in. And I think if you just if you don't have immediately this self-similarity, you might be able to solve it on some by some constraint on some subvariety of vector bundles. So I think you should look into that. But anyway, with Nick Bennis, we just constructed some solutions for the case of 2 or 3 Stokes sectors, which should correspond to KdV and Kp. As for the resulting Painlevé, which was the other question I asked you at the beginning, how, should I expect Painlevé 1, Painlevé 2, Painlevé 3, why? I think that Krichover method doesn't add anything, because the self-similarity, he gives it to himself. And by the time you're here, you know which Painlevé equation you're going to satisfy. So I think it's more of a geometric construction in which you can use P1 or you can use any Riemann surface. And in this way, I think that you can solve that differential algebra question I asked you from the Flaschka paper. Can I construct completely algebraic solutions to the question commutator of 2 operators L comma B equals L? I think you can construct solutions using geometry. At least you can construct them to produce, again, solutions to KdV as had been done before. Now, the aspect of isomonodromy then, how is it completely understood? Okay, so first of all, I wanted to find Painlevé 6 for some reasons which I get to in 2 minutes. And I had started with, in the most naive possible way, in the stupidest possible way from my point of view, I had asked, looking at Kp, just because Kp is the mother of all the isospectral equations, I thought it might correspond to the mother of all isomonodromic equations, which is Painlevé 6. And I was completely wrong, as I'll justify in a moment. So I was finally very pleased when I found Painlevé 6 in isomonodromy, which, as you all know, comes from the Schlesinger problem. And so I thought I would write it down. This was done by the Sato school in the early 80s. And it's very similar to what Flaschka and Newell had done by hand, which I just showed you. they interweave two conditions on the eigenfunction. One, which is a condition on the spectral parameter, and another one, which is condition on the derivative in the spectral parameter. And they do it this way. So suppose you start with this isomonodromy problem, like the Schrödinger problem, a condition on ordinary differential equations. And here you have to take 2 by 2 matrices if you want to find Paine-Levé-6. Then you construct your eigenfunction and you feed it the spectral parameters, you feed it the isospectral parameters by hand through the exponential. Then you have this integrable PDE in the times just by fiat, because the operators are constructed from the eigenfunction. But you also make it so that it satisfies an isomonodromy problem by construction of the eigenfunction. And because it solves both the isospectral and the isomonodromy problem, let me show you what's the significant equation here. The significant equation is, see, this is what the eigenfunction does in lambda. The significant equation is this one. The derivative in time of this matrix lambda equals the derivative in lambda of this matrix with the parameter t's plus the commutator. This is now a commutator not in T1 and T2, which would be the Hamiltonian property, the zero curvature condition. This is a commutator in T and lambda. So this is the trick. For me, it's completely a trick that the Kyoto school found, and then you come up with Paine-Levé-6, starting with the Schlesinger problem, and you also have isospectral deformations. But what isospectral deformations? Not KP. So to me, there still is not a dictionary. It's a trick. It's a trick by creating an eigenfunction that has got times and has got lambdas in it, the isomonodromy parameters. And they prove it by using the tau function, by showing that because of the deformation equations as they were written as isomonodromy, a certain form is closed. Because that form is closed, you can write a tau function for it. You can write it. You can write that form as d log tau, and then just by definition, that tau satisfies the isospectral condition in the times. That's the tau function of the KP hierarchy, but not of the KP hierarchy because you had 2 by 2 matrices. So here is the conclusion of my case study. Finally, in 2007, someone came up with a complete Paine-Levé-6 equation with all the parameters that they were able to associate to an integrable system of PDEs, and it wasn't KP. And this is why I was so stupid. I never should have expected to find Paine-Levé-6 from KP, because as you saw in the KP, in the Krichever construction, there are only 2 singular points, and Paine-Levé-6 has all 6 singularities regular, and it is the mother of all the other Paine-Levé equations because you can view the other ones as confluences of these singularities, and they become irregular singular points. So where does Paine-Levé-6 come from? And finally, Kakei and Kikuchi in 2007 produced it as a self-similarity problem for a 3-wave resonance system, which in algebraic geometry corresponds to a multi-component KP, 3 points at infinity on the algebraic curve. So you can still use theta functions if you want to. This is how they set it up. They set it up using, of course, the Heisenberg subalgebra of some loop algebra, as you normally do in integrable PDEs. They find the similarity conditions by multiplying by a parameter lambda in a clever way. You now have a 3 components, so you have 3 types of time deformations, 1 to 3, and then you have an infinite hierarchy of time deformations in J. They find the similarity equations. They therefore reduce to an ODE. The ODE is a Schlesinger type 3 by 3 matrices. These deformation parameters give you all the parameters in Painlevé 6. But how do you show that you find Painlevé 6? By a Laplace transform, of course. Haven't I been advocating a Laplace transform? As Harna and Mazzacco did previously, you can reduce a 3 by 3 matrix problem to a Schlesinger problem by doing a Laplace transformation. The resulting Schlesinger equation has a column of zeros, and if you reduce to that subspace, you can reduce to a 2 by 2 system, which is Painlevé 6. So that's the end of my case study. Okay, so now in the remaining 5 minutes, I can show you the new project which I was now able to complete. And this is completely an idea of Frank Nyoff. It's a very original idea to generalize Painlevé in a very dramatic way. So let me show you the previous transparency. In the concluding remarks of this paper, Kakei and Kikuchi say that they, instead of using GL3, they could have used n by n matrices and do the endpoint KP differential equations. And if they had done that, they would have found, instead of Painlevé, the Garnier generalization. So what did Garnier do? In his thesis, he proposed generalizing the isomonodromy problem to instead of just 3 regular singular points and 1 apparent singularity, which, as you know, corresponds to Painlevé 6, any number of singular points, again order 2, and then there should be a certain corresponding number of apparent singularities. So when you do this isomonodromy problem, how do you come up with a solution? So Garnier showed that you can equivalently write, equivalent to this isomonodromy problem, a system of PDEs in these apparent and these actually regular singular points. And this is the system of the PDEs. He writes 2 polynomials, and phi and psi, which, as you see, encode the t's and the lambdas. And then he writes this system of PDEs which don't fit in 1 page. Okay. Now, Frank Nyoff's idea, and he gives credit to Garnier between the lines, is that if you fix one of the t's, you can reduce the system to an ODE. So what should this ODE be? It should be some significant ODE of Painlevé type. And it should actually be the beginning of a new Painlevé hierarchy. Okay, so this is the project I failed to be able to complete. So Frank had another significant idea. In an early paper, he did a paper which predated the entire study of Painlevé conditions. Richard Fuchs took up the problem posed by his father of isomonodromy for this equation and showed that it's equivalent to Penlevé 6 by, by this idea. He said, if I introduce a new variable u, not the Laplace transform this time, I'll give you a break. Putting the lambda, the apparent singularity, in the integral and doing, the inverse problem for the Weierstrass P function, and then if I take the derivative in lambda, I then can, in T of this system of incomplete periods for genus 1, I then find an equation equivalent to Penlevé 6. This is completely out of the blue. I don't think anybody understands it, except that Manin says that this is the mirror. This is a proof that there is a mirror manifold to the plane. This is a paper that Marta Marzocco had showed me years and years ago. So can we do the same thing for just one more minute? Can we do the same thing for the Garnier system, and in order to find some ordinary differential equation on a family of curves, more precisely on the incomplete integrals on this family of curves, that would give us this condition equivalent to isomonodromy? Not me, but Frank had proposed this problem and some ideas, and together with Viktor Renolsky, who has written some equations for an explicit sigma function, using what our guess was. Our guess was that with all these, this is the case n equal 2, that with all these parameters, the regular singular points and apparent singularities, of which now there are 2n, we should produce a hyperelliptic curve of genus n. And using the sigma function, which is an adaptation of the theta function for that curve, which we know rather explicitly, we should take the derivatives in these now branch points of the curve, the derivatives of the incomplete periods, all the integrals of the differentials of the first time around the periods. I found that Dolin, Richter, Veselov, and Balkans had used these explicit equations for the periods, but that's for the complete periods, very recently, to find an ODE of order 4. Frank expected an ODE of order 4. And so this is the crowning result. This is our ODE of order 4. If it looks like an ODE of order 4 to you, well, there's the order 4. On some complicated expressions, algebraic expressions of the branch points of the curve. So why is that not complete? Well, because we haven't proved that that's equivalent to the isomonodromy of the problem. But so the idea would be to stare at this equation and stare at the Garnier system for conditions of isomonodromy, and maybe be able to come up with this generalization of Penlevé. Thank you. I can't hear.
So, if you have questions, if you can speak loud, or perhaps tell me now, because you can't
It's
hear
not
very well
matter
this
of loud.
morning.
You know, when you fly, you just have this.
Maybe one question, if anybody has it.
Does it make much of a difference in this case to consider the scalar isomonodromic problem or the first, the non-scalar?
Oh, So I hadn't thought of that, but in view of all the examples, and actually I was very humbled that KP was a 3x3 problem, Penlevé 6 was a 3x3 problem, and or traditionally a 2x2 problem, and I was expecting it to be scalar. So in this case, we don't have an isospectral problem. We just have an isomonodromy one. So it might make some sense to do a change of variable and bring this into a matrix problem, right? Because this is scalar, right? So we haven't thought about that at all. We were trying to go to the algebraic geometry now. Mm-hmm. But I would really love to have a more constructive way to go from isomonodromy to isospectrality, and that certainly should happen with the multi-point KP equation and constructing these eigenfunctions more explicitly. Something I forgot to tell you about is one of these really intriguing remarks of Flashka and Newell. They said, beware that it is not possible to find an integrable PDE for all the Penlevé, for all the ODE problems that have the Penlevé property, because Newell gave a classification or characterization of those in terms of certain properties, and they can show that there are some of those ODEs that have the Penlevé property which do not come from a self-similar reduction of a PDE, just by properties, just by qualitative considerations. So there can't be a one-to-one correspondence. But thanks for the question. Changing variables and going from matrices to scalars seems very interesting.
Any more? Let's thank the speaker for this very